Welcome back. We're now in Module 8, Interpolation, Spatial Statistics. Pretty exciting stuff. In the last video of the last module, I talked about resampling. Remember that resampling kind of looks like this, where you have an input data set, raster data set, and an output raster data set, and for whatever reason, the output and the input don't line up properly. Either the cell sizes are different, or the orientations or the corners of the cells are different. So what you need to do, since you have a new raster that's going to have new cells and new centers of the cells, you have to estimate what the value of that new cell should be based upon values of the surrounding cells in the input raster. So really what you were doing when you did resampling was you were doing spatial interpolation. In general, what spatial interpolation is, it's the process of estimating values. Remember, these are going to be estimates only at unsampled points, or points you don't know the value of, based upon known values at surrounding points. So that's what interpolation is about. We're going to talk about five different types of interpolation over the next couple of videos, and what's good and what's bad, why. So I'm going to use this same data set as an example for a lot of these, and it's basically going to be the state of Utah. And so this is a nice graphical map of Utah. Those of you that haven't been to Utah maybe don't know, but there is a ridge of mountains, the Wasatch Front, that goes down this way. There are Uinta Mountains over here, and there are the mountains down here. So we have high elevation kind of going down the center of the state. We have lower elevation over in the northwest. We have a lower elevation area in here, or lower than the mountains, and we have some more mountains here. So what we're going to do in this example is we're going to assume we don't have all the elevation information for Utah, but all we do have are points where the airports are located, and those airports have elevations. So what we're going to do is we're going to interpolate using these airport elevations and try to get as close as we can to this, which is the digital elevation model, the DEM for Utah. Okay, so if our interpolation really works well, we'll be able to get something that looks like this raster model, which has got very small cells and the elevation precision is really good. Okay, but think about this. If we use the DEM that we can get from the National Map Viewer, where maybe the cells are 30 meters on a side, or maybe even 10 meters on a side, we're going to have so many cells in Utah that this raster data set is going to be huge. So for this example, we're going to use a data set that's got larger cells, and I haven't shown you where to get that yet. So I'm going to show you where to get these two data sets that you can do this example on your own, because you can get this out on the internet. Okay, so interpolation is going to estimate something, which we're going to call this a really good estimate, which would be our raster data set. We're going to see how good these other methods work. Okay, so where am I going to get the data for this stuff? Airports and the digital model with large raster cells. Let's look at the large raster cell model, the elevation model. Before we went to the National Elevation Data Set, NED, that you could access from the National Map Viewer. But you can get larger resolution elevation information for the entire planet, or most of the entire planet, by utilizing NASA's information. And NASA has a bunch of satellites out there that have compiled a bunch of elevation information, and among other things, you can go out and get elevation from NASA. You can get a bunch of other data too. So this earthdatanasa.gov is going to point you to a lot of data that comes from satellites. It's so much data that they've broken up the places where the data is stored into a whole bunch of different centers across the United States. One of those centers is in Oak Ridge National Laboratory, and that's for biogeochemical dynamics. And this is where you'll be able to get the elevation data. So when you go to that site, you'll be able to see that you can download 30 arc-second elevation data for the whole globe. And this 30 arc-second are cells that are about 1 kilometer across. So instead of 30 meters or 10 meters, we're 1,000 meter cells. So we're going to have a more reasonable sized data set to use for our example. So that's where you can get elevation data for the entire planet, 1 kilometer resolution. Where do we get these airports? Well, we can get those from the National Map Viewer. What I've done here is I've told it to download and selected the state of Utah, download by states, select the state of Utah, You download it, you can see that there's an option for geographic names. And what that is within the state of Utah, it's all the places that have official geographic names by the geographic naming system. So you can download that. It's going to be a bunch of points, and some of those points are airports, and so you get the data set that's airports. Okay, so we're set up to do the example. Back to interpolation. We're going to identify a value at a new location or estimate that value based upon values at some number of nearby locations. There's different kinds of interpolation, so if we're going to use the terminology, there are global interpolators and there are local interpolators. Global interpolators are going to use all the points, all of the airports in this case, to come up with an estimate. Local interpolators are only going to use a subset of all the points, and generally those are going to be the ones that are close to the points you're interested in. There are exact and approximate interpolators. Exact interpolators, the points in the interpolation are going to have the exact same values as the points in your input. So in this case, at the location of an airport, your interpolation will give you exactly the value of that elevation of the airport. Approximate is going to kind of fit a curve to all your data, and so it may overshoot or undershoot the input data. Deterministic and stochastic. Deterministic, you can think of that as based upon an equation. You can run the equation 10 times and get exactly the same value each time. Stochastic has some random variation in it, so if you run it 10 times, you might get 10 different values. For all of these, remember Tobler is going to be important. Remember what Tobler said, everything's related to everything else, but closer things are more related than things that are further apart. Okay, so the first type we're going to consider is trend. And what trend is going to do is it's going to fit a surface to all of the sample points. So in our case, we're going to use all of the airports, which means it's going to be a global interpolator. We're going to fit a surface to all of the airports. You can fit different orders of polynomial to your input. So in this example here, you see a graphic that represents reality, and this would be a first order or a plane that's fit to this surface. And you can see that we have points here that are the points we're going to use to make our estimate. And what a first order polynomial does is it fits a plane to these points that minimizes the distances, the sum of the distances from the point to the plane. Here would be a second order polynomial. This would make a U-shaped polynomial. Again, you can see that in addition to using all the points, it's not an exact, it's an approximate interpolator, because some of the points are above and some of the points are below the surface, so the interpolation is not going to match the input at all the points. So it uses regression. It minimizes the distance between the points and the surface. You can use ArcGIS. You can go up to 12th order polynomials. That's usually not a very good idea. Here's our example. We want to get to this depiction of Utah using a first order global interpolator. So we're going to interpolate and just get a plane to fit for all that data. That's what this looks like. So this is a plane. This would be the highest elevation. So this side would be tilting down towards the lowest elevation there. So a first order polynomial isn't going to fit data that obviously isn't basically flat or tilted in a uniform way. Here's a second order. Now what would second order look like? It's going to be like a U or an upside down U. In this case, it's like an upside down U. So the highest elevations run along this axis here, and the U then slopes down in both directions. So that does a better job of showing this mountain range, this kind of frame of Utah, the backbone of Utah here. Let's go to a third order. Third order looks like this. And you can see that this third order is able to grab these east-west oriented mountains and get a depiction of those over here. And it's able to get these higher elevation points in here. So now we have a third order polynomial, and it gets harder and harder to visualize what the polynomials look like as you go to higher and higher orders. Okay. Trend is global. It's going to use all the points. It's approximate. It's not going to match the input elevations, or in this case, values of exactly. And it's deterministic. You can run it 100 times and get the same answer on it. This is a statistics table for the DEM, which is what we're trying to match. And when we run the first order model, you can see that there's something down here which is an RMS, root mean square error. It's estimating how far it is from the points to the surface. So this is 1146 for first order. Second order is 1103. So second order is a little bit better in terms of RMS error than first order. Third order has an RMS error of 1070, which again in theory is a little bit better than second and a little bit better than first. At some point the absolute values of these RMS errors mislead you into believing one might be better than another, but at some points it's okay to use this as an estimate of quality of fit. Okay, the next one's called inverse distance weighted interpolation. This one fits Tobler's first law really well. What it's going to do is it's going to give a higher weight in the interpolation to points that are closer to the point you're looking at. So the influence of points decreases the further away you get. So things that are more related are closer to each other. Things that aren't related as much are further away. This is a graphic that shows values that are projected onto a raster. This would be a value of 20 that's 12 units away from our unknown point. This is a value of 10 that's 4 units away from our unknown point. So we're going to apply a higher weight to the value of 10 because it's closer than we are to the value of 20 because it's further away. This is another example that shows you this projected down onto a flat plane, and the way it's calculated is you take the value and you divide it by the weight for that value, and the weight is dependent upon the distance between the unknown point and the known point. So 34 is 1 unit away, so that's the 1. 22 is 4 units away, so that's the 4. This exponent here is called the power, and what's going to end up happening is the higher the power, the more rapid the influence dies out with distance. So if you have a higher power, closer things are more important than further away things. And then you divide it by the sum of weights, and that gives you the interpolated value. So in this case the interpolated value is 32.38. So there you have it. This 22 doesn't count as much because it's 4 units away. So the power is the relative influence of distance. The higher the power, the more importance closer points get. You can tell this method to either pick a number of points or by a radius. So you can go out a certain distance and pick all the points that are within there and include those in your equation, or you can say I just want the closest 4, the closest 6, or the closest 8, and it'll go out and find those closest points and include those in the equation. What this method tends to do is it cuts off peaks and fills in valleys, and so this kind of shows that graphically. If there were a higher peak in here, it would cut it off. If there were a lower valley in here, it would smooth it out. So it kind of smooth things out, is what it does. It doesn't really work well with trends, and you can imagine if you had a trend, then everything on one side of your unknown value would be higher valued, everything on the other side would be lower valued, but they'd be the same distance, and so the weights don't work out very well with trends. Okay, so in this case we're going to use a power of 1, which means nearby and far points are basically going to have kind of the same value, the same influence, and we're going to pick the nearest 12 neighbors, so we're going to pick the nearest 12 airports. This is what we get. So again, we see some high elevation in here, so this seems to do better than at least a first order trend. Let's go power of 1, 6 neighbors, so we're not going to count as many nearby points. We get this. Now we're going to increase the power, which means we're going to increase the influence of nearby points, and we're going to pick 12 neighbors. We get this. Here we start to see lower elevation information that didn't show up before, and we see some more high elevation discrimination we didn't see before. Power of 2, only go out 3,000 meters to find things. Okay, so in some places where there aren't a lot of points, you're not going to get a very good interpolation, because by the time it goes out 3,000 meters it may not find any points. It's not able to do anything. Okay, that was 2 basic methods for doing spatial interpolation. Trend gives you a quick idea whether there are trends in your data. first, second, third order is pretty reliable. More than that is kind of less reliable. And inverse distance weighted, which is Tobler's maximum theory, which is closer things are to each other, the more important they are. Further away they are, the less important they are. Next time I'm going to talk about a couple more. I'm going to talk about spline, which basically fits a curve to the data, kind of like a trend, but it's not a trend that's global, it's a local trend. And the other one I'm going to talk about is natural neighbors. So that'll be next time.